So, hi everyone, I'm Audrey Smargiassi. I'm a professor at the University of Montreal and I'm the co-lead of the Canoe Noise team. I'm going to present the work that the Noise team has done with Canoe, and a lot of it was done by our amazing postdoctoral student, Ying Liu. And there were other members of the team who also contributed to the work, including Tor Oyamo, Daniel Rainham, and Dave U. Davies, and other members as well. So I'm going to present the work of the Canoe Noise team. So most of the work, as I mentioned, has been performed by Ying Liu and in collaboration with other members of the team. So the noise group wanted to develop estimates of environmental noise exposure for populations of Canadian cities. And so what we did is we gathered noise measurements for Canadian cities, and then we estimated noise levels for residential postal codes of Canadian cities using those measurements and statistical models. We also explored various models to improve our modeling effort, and we increase the noise monitoring available for Canadian cities, and it also explored the use of smartphones to measure environmental noise. So here we have the noise measurements that we use to estimate noise levels at residential postal codes of Canadian cities. So we used about 700 noise measurements for 5 Canadian cities, so Toronto, Montreal, Vancouver, Halifax, and Longueuil, which is a city in the suburb of Montreal. So you can see that the noise measurements were taken on various years, spanning from 2003 to 2018. Measurements also were for different seasons, and they were also taken usually over 1 to 2 weeks, but in Vancouver, measurements were only for a few seconds, but all measurements were considered estimates of daily noise levels. So you have like the locations of the noise measurement sites in the various cities in the figure to the right. So what we did is we predicted those noise measurements using predictor variables that were common to all the cities. So we did not use all available predictor variables. We used predictor variables that were common to all cities because we developed a global model. So all predictors were the same for all cities. So what we did is we used predictor variables to predict the 700 noise levels. And with the model, the statistical models that we've developed, we then predicted noise levels everywhere else at all other postal codes where there were no noise measurements. So among the predictor variables, we used traffic flows that were based on origin destination data. We also used other source-related predictor variables, such as the distance to noise annoyance aircraft contours, the NEF contours. We actually used also points of interest, such as the number of fire stations within various buffers around the measurement sites. So we used buffers from 50 to 1,000 meters. And other predictor variables such as the greenness indicator, NDVI, or population density. So we used the 700 monitoring measurements. We used those predictor variables And we used two different statistical models. We used a more traditional regression model, which was based on GAM, a GAM model, a land use regression model. And we used a random forest model. This model had a better performance to predict noise levels because it's actually more suited to consider complex non-linear relationships. So using those predictor variables, noise measurements, and models, we predicted noise levels at the postal code of the 5 cities. And so the predictions are best for the years of the measurements. So measurements in Vancouver were for the year 2003. So the estimates that we've produced are better to be used for years close to 2003. So the modeling effort is presented in the publication by our postdoctoral student Ying Liu in environmental pollution in 2020. So here is an example of the data set and the metadata. So you basically, what is provided through Canoe is an Excel file, a CSV file with the postal codes, the latitude and the longitude, and then you have 2 estimates of daily noise levels, estimates from the random forest RF model, and estimates from the land use regression model for the various cities. And you have the year, the best year to apply, the year for which the noise level should be applied to. So of course you could use like the estimates for other years, but it is believed that the estimates would be more accurate for the years closest to the measurement period. So then here you have the data set. So you have on the left the estimates of noise levels from the random forest model and the land use regression models for each city. So to the left, it's the random forest model. To the right is the land use regression model. And those estimates are also summarized to the right in the panel with the box plots. So you can see that noise levels were highest for residential postal codes of Montreal and Longueuil. Longueuil is just here to the south of the island of Montreal. So then, of course, there are limitations to what we've done. So related to the sampling campaigns across the 5 cities, the measurement durations were variable. The estimates were also for different years and different seasons. There were even different noise meters that were used in the various cities. We also used an imperfect database of predictor variables to predict the noise levels at the residential postal codes, because we used predictor variables that were common to all cities to develop a global model. And so we also did not have commercial truck mobility data as a predictor variable. And in our statistical models, we did not include the influence of the building height. So the building height in 3D was not considered in our statistical models. And we only had 1 year of measurement in each city, and we had a limited number of sampling sites. So yes, what we've done has limitations, and we've tried to improve our work. So what we did as a next step, and again, the work of our postdoc Ying Liu, it's now published in Environmental Research in 2021. So what we did is that we used the propagation model sound plan to consider the reflection of the noise in 3 dimensions, so the influence of the building height, for example. So we use SoundPlan to estimate noise levels from road traffic, considering, as I mentioned, the reflection in 3D and the ground attenuation. Now, using this noise surface, the traffic noise surface from the propagation model, what we did is we computed the difference between the measurements at some locations and the estimates from SoundPlan at the same locations. So this difference, the residuals, was considered to represent what was not considered by the SoundPlan models. So the other noise sources that were not considered in our propagation model were expressed by the residuals. Now, we only had the residuals at the measurement sites. So what we did is we modeled a surface. So in all locations, we modeled those residuals using some variables and a random predictor variables and a random forest model. So we then obtained a surface of residuals and the surface of traffic noise from SoundPlan, and we added those two together to improve our estimation of noise levels, thus considering, namely, the building influence. But there are also limitations to this approach, this hybrid model data set. Well, the same limitations as our previous effort. We did not consider commercial truck mobility. We had a limited number of measurement sites and for limited number of years. Additional limitations, such as the fact that we used traffic flow data both in the SoundPlan propagation model and in our estimation of the residuals, and thus there may be some overestimation of noise levels on roads. So although there was some improvement in our modeling of noise levels, there are also additional limitations, such as the fact that the estimates are not realistic, because as you can see, the scale goes up to more than 100 decibel A on major roads. And this is due to the fact that we arithmetically added the residuals to the noise levels from the SoundPlan model. So while this model may provide better contrasts, spatial contrast and noise levels, there are a number of limitations that are related to that as well. So the noise team also aimed to increase the number of noise measurements in Canada. So this work is currently done by Tor Oyamo, a member of the noise team. So more than 150 measurement sites were or measurements were taken at more than 150 locations in Ontario, in not only in large areas, actually in the smaller cities such as Kitchener, Waterloo, and in the suburbs of Toronto, such as Mississauga. And this data will be available to develop similar models as those that we have done previously. And as I mentioned, it's interesting that we are now trying to cover smaller cities and not only large cities such as Montreal, Vancouver, and Toronto. And lastly, and this is the work of Daniel Rainham and his collaborator. So we are exploring the use of smartphones to estimate noise levels. So there is currently a scoping review underway to look at the use of smartphones to measure environmental noise. So more than 30 articles have been included in the review, and a number of parameters are currently assessed, such as the operating system or microphone use and so on. And there's also some measurements in real living conditions that are going to take place this summer by Daniel's team. So yeah, the noise team has developed a data set of estimates for 5 Canadian cities that are now available to look at associations with various health outcomes. And the team is also planning on improving the modeling of noise levels for the Canadian population.